Hi, in the textbook Linear Algebra and its Applications by David Lay, there are many true-false questions. We will give the answers for those questions. We use the fourth edition of this book. Today, you may find the new edition of this book. Questions in section 6.2, orthogonal sets at page 345. In problems 23 and 24, all vectors are in Rn. Problem 23. A. Not every linearly independent set in Rn is an orthogonal set. 2. This set is a linearly independent set in Rn, but it is not an orthogonal set. If Y is a linear combination of no-zero vectors from orthogonal set, then the weights in the linear combination can be computed without row operations on a matrix. So, thus we can use this formula to compute the weight Cj. C. If the vectors in an orthogonal set of no-zero vectors are normalized, then some of the new vectors may not be orthogonal. 4. Thus, if u dot v equals 0, then the normalized u dot v also equals 0. D. A matrix with orthonormal columns is an orthogonal matrix. 4. Orthogonal matrix is a square matrix. If L is a line through 0 and if tangent y is the orthogonal projection of y onto L, then the length tangent y gives the distance from y to L. Fourth, from this figure, we see the orthogonal projection of y is this one. Then this is the distance from y to the line L given by the length of y minus y hat. Problem 24. A. Not every orthogonal set in Rn is linearly independent. 2. Example, this is an orthogonal set in Rn, but it is a linearly dependent set. If S is an orthogonal set of no-zero vectors in Rn, then S is a linearly independent set. B. If a set S equals U1 to UP has the property that Ui dot Uj equals 0 whenever Y not equal J, then S is an orthonormal set. 4. Orthonormal set U1 to UP is not only having this property, also should be the length equals 1 for all vectors in this set. 3. If the columns of a m times n matrix A are also normal, then the linear mapping x to ax preserves length. 2. Thus we have this one. V. The orthogonal projection of y onto V is the same as the orthogonal projection of y onto CV whenever C now equals 0. 2. Because we have this one. E. An orthogonal matrix is invertible. 2. The definition of an orthogonal matrix. An orthogonal matrix must be invertible. Questions in section 6.3, orthogonal projections at page 353. In problems 21 and 22, all vectors and subspace are in Rn. Problem 21. A. If Z is orthogonal to U1 and to U2, and if W equals span of U1, U2, then Z must be in orthogonal space of W. 2. If Z dot U1 equals 0 and Z dot U2 equals 0, then Z dot the linear combination of U1 and U2 is 0. B. For each Y and each subspace W, the vector Y minus project WY is orthogonal to W. 2. In this figure, the vector Y here and the project Y is here in the space W. Then the Y minus project WY is here. This is orthogonal to W. 3. The orthogonal projection Y of Y onto a subspace Y can sometimes depend on the orthogonal basis for W used to compute Y hat. 4th, the orthogonal projection of Y onto W is the closest point in W to Y. It does not depend on the orthogonal basis. 3. If Y is in a subspace W, then the orthogonal projection of Y onto W is Y itself. 2. If Y is a linear combination of an orthogonal basis of W, then Vj is given by this one. This leads to the orthogonal projection of Y onto W is Y itself. If the columns of a n times p matrix U are orthonormal, then UUTY is the orthogonal projection of Y onto the column space of U. 2. Thus we have this one. Problem 22. A. If W is a subspace of Rn, and if V is in both W and W perpendicular, then V must be the zero vector. 2. If V is in W and V is in the orthogonal space of W, then V dot V equals 0. This implies the norm of V equals 0. So V must be the zero vector. B. In the orthogonal decomposition theorem, each term in formula 2 for Y is itself an orthogonal projection of Y onto a subspace of W. 2. At page 358, we see that formula. Well, Wi is the space spanned by the vector Ui. See, if Y equals Z1 plus Z2, well, Z1 is in a subspace W, and Z2 is in W perpendicular, then Z1 must be the orthogonal projection of Y onto W. 2. Thus, the Y can be written uniquely in the form Z1 plus Z2. E. The best approximation to Y by elements of a subspace W is given by the vector Y minus project WY. 4. The best approximation to Y by elements of a subspace W is given by the vector project WY here, not this one. E. If n times p matrix U has orthonormal columns, then U UTX equals X for all X in Rn. Fourth, we have this formula, not this one. Thanks for watching. Bye.